Welcome back all of you. In the last class we discussed about the relaxation. We started discussing, not completely discussed, and I introduced about the spin lattice relaxation and started understanding the various concepts involved in that, especially it is the alignment of or attaining the thermal equilibrium of this magnetization after it is disturbed. This is what I called as attaining thermal equilibrium. This is called a relaxation, spin lattice relaxation, or attaining thermal equilibrium, or T1, where it is various synonyms we discussed also. And I said that this relaxation will happen by the spins giving its energy to the lattice. Lattice, it means, I said, it is not a crystal lattice or a rigid system. It is anything other than the nuclear spins of your interest can be considered as a lattice, or in other words simply the surroundings of the spin system. It will give energy. Spins will give energy. Okay. How it gives energy? It gives an energy in the form of heat. We understood that. And this heat is negligibly small compared to kinetic energy, quickly get dispersed at the body temperature. It is largely gets unnoticed. And then for this to happen, for the system to give the energy and this to the lattice, it must be a stimulated emission. In the sense, simultaneously the spins from the upper state should come to the lower state. Then lattice from lower state will go to the higher state. This should happen simultaneously, only then there is conservation of energy. If both the spins and lattice are in the upper state and come down, it cannot happen because it doesn't conserve energy. For the spins from excited state or upper state to come to lower state, there must be stimulated emission. This spontaneous emission is not possible. This stimulated emission, for to happen, there must be a fluctuating magnetic field. This fluctuating magnetic field comes because of the random fluctuation of the molecule, chaotic motion of the molecules. Electronic or vibration motion, such things have very least effect on this emission of the energy. So this fluctuating magnetic field, because of the motion of the molecular motions, it could be chaotic motion, diffusion, and some thermal agitation, and varieties of random fluctuations could be possible. And these should generate frequency in the Larmor frequency, not any frequency. So there could be a wide range of frequencies present, but all are not possible to simulate emission or give energy of the spins to give energy. It must be only certain frequency to see that the spins will stimulate the spins to give out the energy. That can happen. So it should be the Larmor frequency in the transverse plane. But I also said the transverse plane it is also the Larmor frequency. The external RF is also the Larmor frequency. What is the difference then? The difference is the external RF will excite or affect all the spins uniformly, whereas the Larmor frequency or the RF that is generated due to the fluctuating magnetic field in the transverse plane affect only few spins, selected spins. This is the main difference. Okay. So this is what we understood. We will go further now today and see understand more about the relaxation phenomena. Now frequencies are associated with the random motions of the molecule. What are the frequencies? I told you it is a distribution of frequency. It is not one frequency. There is a random band of frequencies there. And this distribution of frequencies is called a spectral density. It is given by a function called spectral density function. J of omega is the distribution of the frequencies produced because of the fluctuating magnetic field. And also in simple terms you can say this spectral density J omega is proportional to the probability of finding a component of the motion at a given frequency omega. It is in radians per second. Okay. This is simply the spectral density function. It is proportional to the probability of finding component of the motion at a given frequency. That is the concept. You please remember that. Now I will introduce another term called rotation correlation time, tau c. What is the rotation correlation time? It is a frequency associated with the random motion which is characterized by what is called a rotation correlation time. When the random motion is going on, and there is a frequency associated with that, I told you. Not one, several frequencies are present in the band of frequencies, and this is characterized by what is called the rotation correlation time. And what is the rotation correlation time? The definition of it is average time taken by the molecule rotate through 1 radian. That is important. See, the average time taken by the molecule to rotate by 1 radian is called a rotational correlation time, given as tau c. This tau c, j omega, they are all related, they are important. Okay. So, short correlation correspond to rapid tumbling motion and large correlation time correspond to slow tumbling motion. It is understandable. Short correlation time means the tau c is very small, means molecules are undergoing rapidly. So that it undergoes this rotation so fast, and you can find, you can calculate what is the average time taken to rotate to 1 radian. If it is undergoing very fast, means tau c is very short. Okay, short correlation time. On the other hand, when there is a long correlation time, then the molecules are tumbling very slowly. It can happen. You can have a fast moving molecules, take a solution which is little viscous, then tumbling motion is very slow. Okay. In which case you will have a long correlation time, or take simply isotropic solution like water in a bottle. Their tumbling motion is much faster and it has a short correlation time. So, short correlation time, whether short or long, depends upon the tumbling motion of the molecule, whether it is rapid or slow. This is the important point. So, the spectral density function now can be generally defined by a general form, a simple form, general form. It is given by spectral density function j omega as 2 times tau c over 1 plus omega square tau c square. So, that is why I introduced the term tau c as the correlation time, rotation correlation time. I introduced j omega, that is the spectral density function, and now this spectral density function can be correlated to correlation time, the motion of the molecule, given by this expression. Now, you remember it has a maximum at omega is equal to 0, and the spectral density drops off for higher and higher frequencies. How fast it drops off is controlled by tau c, correlation time. So, this you must remember, the spectral density function has a general form given like this. It depends upon tau c, and the spectral density function has a maximum at omega 0 equal to 0, and then it drops off at higher frequencies, which is controlled by correlation time tau c. And now, correlation time, I told you about the motion of the molecule. It is the average time taken for the molecule to undergo rotation by 1 radian. Now, that means it depends upon the size of the molecule also. For example, depending upon how small or big the molecule, the correlation time depends, where it varies. Depending on the frequency of the molecular motion, tau c can be smaller, equal to, greater than, or larger than omega frequency. That is very important thing. It depends upon tau c, and tau c depends on the size of the molecule. The distribution of the oscillating frequency due to dipolar wave interaction varies with tau c, because it depends upon the size of the molecule. Okay. Now, the total amount of the oscillating fields is constant, but the upper limit of the frequency varies with correlation time. That means the total amount of oscillating field you have got, total frequency, total amplitude is constant, area of the curve if you take. But the upper limit of the frequency vary with correlation time. Very interesting thing. It can be understood by a graph like this. See, for example, I have given 3 plots here, one in green color, red color and blue color. Green color corresponds to slow motion, very slow motion. That means the maximum of j omega is here and drops are very fast. In this region, it is very small, almost very slow j omega is practically very small, close to 0, and j omega is maximum only in this region. See, it is as a function of omega we are plotting. If you consider this one, the red one is something interesting. It is in between these two. Okay, the red one is in between these two, and then what is going to see the intermediate motion. It is not slow or too fast. Okay, and the blue one is something, it is very fast motion. Very fast motion. See, at even it is almost uniform all through. See the difference. At slow motion, j omega is larger here, amplitude is larger, and intermediate motion it is spread over a large range, j omega, but then drops off very fast. In the fast motion regime, it is more or less, it is equal all along. It it not drop, it drops off only very small at the end. Okay, but the area of this j omega, as I said, oscillating field, total amount of the oscillating field is always constant except for this upper limit is varying here. You take this area or this area or this area, all are same. The total oscillating field remains constant. But interesting thing, when does it happen? You should understand. This is the situation, omega tau c is larger than 1 when omega is the Larmor frequency and tau c is the correlation time, it is always in nanoseconds. You multiply these two, if it is very much larger than 1, then the j omega will be in this region. If omega and tau c both you multiply Larmor frequency with the correlation time, which is in nanoseconds, Larmor frequency is in megasecond, megahertz, like a 500 megahertz, 500 into 10 to the power of 6 or 5 into 10 to the power of 8. And tau c is in nanosecond, 10 to the power of minus 9. So it can so happen, you multiply this, it comes close to 1, let us say. In which case, so happens, the intermediate region where it is 1, omega tau c is equal to 1. In which case, this is what the curve we are going to see. When omega tau c is very much smaller than 1, it is a fast motion, this is the region we have come across. So that means the spectral density function, the distribution of the frequencies, what I showed you now, depends upon the correlation time and also the Larmor frequency. So many things are involved now. You understood? We discussed about the molecular thing, we discussed about fluctuating field, we say it is a spectral density function, that depends upon the tau c. Now omega into tau c together depends upon the j omega. So these are the things. So please remember, the j omega, omega tau c is larger than 1, the j omega has a maximum here and then tapers are very fast. When omega tau c is exactly equal to 1, it is the intermediate situation. When omega tau c is very much smaller than 1, it is fast motion. Fast motion should be having omega tau c very much smaller than 1. The rate of relaxation is determined by the intensity of the fluctuating field. That is important. Okay. So for small molecules and especially in the low viscosity solvents like very low viscosity, then motion is faster, right? When tau c is very small, molecular motions are very fast. Small molecules and especially in the low viscosity solvents, molecular motions are very fast and j omega has relatively very small component, the Larmor frequency. Please understand this statement. Molecular motions are fast, for tau c is small, j omega is a relatively very small component at the Larmor frequency. So the relaxation is slow. That means it takes long time for spins to relax. T1 is longer. T1 value is very long. It could be of the order of several seconds, sometimes minutes, sometimes much larger. This can happen for a small molecule, especially when the molecular motions are very fast, j omega is relatively small component. Okay. Now, this is a condition what we call as extreme narrowing limit. When tau c is small, T1 is longer, this is called extreme narrowing limit. Okay. Then you can see here in this case, in the case of this one, slow motion and fast motion we discussed. Here we are considering a molecules are motions are very fast. Fast motion we are concentrating on this condition. This is called extreme narrowing condition. Now for medium sized molecules, omega tau is approximately equal to 1. I told you tau c in nanosecond, omega 0 is in megahertz. Now multiply these two, if it is of the order of 1, the tumbling rate decreases. Molecules do not tumble very fast like previous case. Spectral density at omega 0 initially increases and then falls off as soon as for slow tumbling motion, then it falls away. As very important thing, initially it increases and then falls away after some time. So this is the situation for omega tau c is equal to 1, it is in an intermediate state. The T1 has a minimum in the intermediate rate. You understand, in the previous case T1 was long, when omega tau c was, you understand what I said here, when omega tau c was not here, okay, T1 was long here as j omega has very small component. So this is extreme narrowing limit. But omega tau c is equal to approximately equal to 1. T1 curve has a minimum at it and at intermediate rates. for very small and rapidly tumbling molecules. Another thing, rapidly undergoing motion, more faster motion. Under this condition, T2 is equal to T1, and relaxation is slower and the line widths are narrow, very narrow. This can happen only in solutions, especially in low viscous solvents. In solutions, it so happen you will come across a situation, relaxation is slower and line widths are also narrower, and that is the situation. T2 is equal to T1. What is T2? I will not discuss. It is spin relaxation, another term, another relaxation phenomenon. We will come to that later. Under this condition, both relaxation phenomena is approximately equal to, not exactly equal, approximately. I have to put the word approximate. Approximately T2 is equal to T1 is a rapid tumbling motion. You can look at this graph. T1 values as a function of correlation time. See, in the slow motion this is the region, and the fast motion region it goes up again. The intermediate motion is here, and then we will let us worry about T1. T2 will come to that later. In the T1 curve comes like this, decreases and then increases. It initially decreases from slow motion as you keep on increasing the tau as a function of tau. At the intermediate motion almost reduces drastically and then goes up again. This is the fast motion. So, it forms a curve like this. This is the intermediate case. So, at both for slow motion and for fast motion T1 increases. Very important thing, T1 relaxation is very sensitive to slow motions and also here and also fast. However, T2 relaxation may still be stimulated by them. That is also possible. T1 can also, the slow motion can still cause T2 relaxation. We will discuss that later. Now, I want to introduce a term how this T1, is it a natural phenomenon, can be controlled from outside. All these things I discussed about the motion of the molecules and then how fast it rotates, tumbling motion, correlation time, spectral density function because the molecular motions we discussed. When can the molecule undergo tumbling motion faster and slower? You know that. So, it depends first on the size of the molecule and depends upon the environment and the size of the molecule also. For example, in a viscous solution, it cannot undergo rapid motion. Whereas if you take a less viscous solvent, just ordinary water you take, molecules will be undergoing thermal agitation very fast. Okay. And if I take highly viscous solution, molecules will not undergo tumbling motion very fast. And also it depends on the size of the molecule. Small molecules undergo rotation very fast, and big molecule cannot rotate so rapidly. You can't ask the elephant to rotate faster like a cricket ball. So, it is possible, right. So, like that depends upon the size of the molecule. But then externally can we control it? Is there a way we can control it? Yes, we can control. It depends upon the solvent and temperature dependency. It is like this. If the viscosity solvent is of the solvent is high, tumbling rate is reduced. That is what I said. And then if this temperature is also lowered, relaxation time is reduced, then signal get broadened. These are related to each other. So, then now you know what to do logically. If the viscosity of the solvent is very high, tumbling is reduced. How do you reduce the viscosity? Raise the temperature, increase the temperature, make sure that molecules undergo motion rapidly. That is one thing. So, when the temperature is lowered, it happens, relaxation time is reduced and the signal will get broadened. Alternately, what you do is raise the temperature. So, it depends upon the solvent and the temperature. You can play with that. See that you get sharp lines. Lines do not get broadened. So, this is possible. The peaks, the signal peaks, signals what you get. If you want to get narrow peaks and not get broadened because of various external parameters, you can control them with the solvent and also by temperature. Now, one may ask a question. So far we have been discussing various things. Now the energy is smaller than the kinetic energy, and I told you it will quickly disperse in the spin system from spins to lattice very fast, and the effect is very little seen at the body temperatures. I agree. Such a small energy. I gave the comparison of pouring hot bucket of water into a big ocean. Fine. If such a small energy is there, system readily absorbs it. It can dissipate very fast. Then the question is, why do spins take so much time to relax? Should it not immediately give the energy and relax faster? That is the next question you have to ask. Why cannot relax faster? Why all spins, some spins takes several seconds, minutes, hours. In some extraordinary cases, it can take days. disturb the spin system, it will take several hours, sometimes days to come back to thermal equilibrium. Why can't all the spins quickly disperse energy and then relax faster? The problem is there must be efficient mode of transfer of energy of the system. Efficient mode of transfer of energy of the system is needed. Then only it can happen. And if the T1 is longer, the suitable fluctuating fields at the Larmor frequency is not present in abundance. Meaning the local fluctuating fields generated at the site of the field, because of the rapid tumbling motion, the fluctuating field is not present abundantly at the Larmor frequency. It is very little is present. As a consequence, spins are not able to relax faster. Energy, it cannot give the energy to the lattice. So that is the important thing. Larmor frequency must be out of the fluctuating field must be present in abundance. Okay. These are the important conceptual points which I wanted to discuss, so that you people are familiar with the concepts what we have been discussing about the relaxation mechanism, idea of relaxation, what are the important concepts involved. So far I was talking about only the relaxation of the spins attaining thermal equilibrium, that is what I called as spin lattice relaxation. Spins lose energy to the lattice and come back to thermal equilibrium. And we understood a lot of things, a lot of concepts, very important points. All these are important to understand. Now we also understand some relaxation mechanisms. The relaxation, one is T1, that's another thing, there is another type of relaxation. But what are these mechanisms which helps this relaxation? In a given molecule, you study, you have a molecule of your interest which you want to study. What are the things which are in the molecule, internal interactions, which can aid relaxation? Mechanism to help the spins to release energy to the lattice and relax. There are several things here. There are several phenomena responsible for the relaxation mechanism. One is a dipole-dipole interaction, that is interaction between the two nuclear spins. Chemical shift anisotropy, which when I come to solids I will discuss what is ESA. Chemical shifts, remember I told you one thing in the beginning, very first class in this course and also in the previous course. All parameters in NMR are tensorial and all of them are anisotropic. You can measure these properties in different directions, they are different. But in the solution state I told you when I discussed about the internal interaction parameters, this chemical shift anisotropy, dipolar coupling, G anisotropy, quadrupolar interaction, they all get averaged out. And especially for spin off system, quadrupolar coupling also won't be there. That is what I said. So, but these are the things system which are present, they are all present in the spin system, but they are all anisotropic in nature. Okay. So, similarly chemical shift is also anisotropic. It may not be present, you may not be able to determine that in the solution state, but inherently that property is there, it can aid the relaxation. CSA can aid the relaxation phenomenon. And molecular translation motion, flow and diffusion if it is there, that can also cause relaxation. And there is scalar coupling that can cause relaxation. Electrical quadrupole coupling, spin rotation, various other phenomena are there. All of them can participate in generating the local fluctuating fields for the spins to relax and give energy to the lattice. So many mechanisms are there. I told you we have to generate the fluctuating magnetic field has to be generated at the Larmor frequency in the transverse plane for the spins to give energy to the lattice and relax. But the sources of this fluctuating magnetic field, I said, is various molecular motions. But internally with respect to the molecule, there are several mechanisms. All of them help aid in relaxation. Okay. So, we will understand quickly some of these relaxation mechanisms. Dipole-dipole relaxation. What is a dipole-dipole relaxation? It is a relaxation mechanism of spin half nuclei, many spin half nuclei. When they come close to each other, they can interact. Because there are two spin tiny magnets, when they come close to each other, there can be an interaction. And that can cause relaxation. It is a dominant relaxation mechanism. This is a dipole relaxation among all the various possible phenomena which are responsible for relaxation. This dipole relaxation phenomenon, that mechanism is dominant. When I go to the next class, I will discuss about NOE. It is also source of NOE. This dipole-dipole relaxation is also source of NOE. Then when I discuss in this chemical shift and internal interaction, I also said this dipole-dipole coupling is not present in the solution state because of the motional averaging. True. You will not be having a dipole-dipole coupling to see, but dipole-dipole interaction will be there to aid the relaxation. This interaction is present. It is not going to create the magnetization for detecting. You will not get dipole-dipole coupling, but it will help the spins to relax. So that will be present. So what happened if you consider two neighboring molecules, neighboring nuclei, they are tumbling in solution, undergoing motion, and you can treat each nuclear spin, this one and this one, as a dipole. These dipole, one dipole comes next to the other dipole. It has this influences the magnetic field at the site of it. Because of this magnet, tiny magnet, there is a magnetic field surrounding it. There are lines of force here affecting this nuclear spin. So this nuclear neighboring nuclear spin feels the field because of the other spin. This can affect and for this there is no need of a chemical bond or anything. It need not. It can be anything, neighboring nuclei, neighboring molecule, they can come close by. And what is happening is, interesting thing is, the orientation of the nuclear spin between them, they will not change. It remains same. But then as it keeps on rotating its place, it keeps on changing the fluctuating magnetic field. See, orientation do not change. Please understand, the orientation of each nucleus with respect to the static magnetic field does not change. This nuclear spin and this is the magnetic field B naught. I will put like this, and with respect to B naught, this is oriented like this, this is oriented like this. If I have another spin oriented like this, that remains same. Orientation does not change with respect to the static magnetic field. But what is happening is, the relative positions in space will vary. Once it is here, once is here, once is here, once here, here, like here. See, let us keep this nuclear spin constant, that position. That position is, assume it, I have kept it constant. Once the another spin is here, next it is here, then comes here, here, here. So it is undergoing rotation. It is undergoing, changing the position with respect to this nuclear spin. Another nuclear spin is changing its position all across. What does it mean? Because this is a magnetic field influencing this, the lines of force at the site of this nucleus change depending upon its position. The local field experienced at one nucleus as a result of the neighboring nuclei will keep on fluctuating as a function of molecule tumbling. The molecules undergo tumbling. When it undergoes tumbling, the dipole-dipole interaction, it so happens, the position of the nuclear spins with two nuclear spins with respect to the magnetic field, the orientation do not change. One nuclear spin is there, other nuclear spin keeps on changing its position all across, retaining its orientation with respect to the magnetic field. As a consequence, the magnetic field at the site of the other spin keeps on changing. It is a fluctuating magnetic field. It keeps on changing as the molecule tumbles. And then this helps the protons which are neighboring to this, or any spin which is neighboring to this, relax. Okay. So, and that is the reason why protons that don't have nearby spins, near neighbors, that is another proton which is close by, which is far away, they relax more slowly. The reason is, if I am relaxing, one proton is next to the other proton, if they are very close by, the spatial proximity is very important for dipole-dipole interaction, then the field experienced at the site of this nucleus, the fluctuating field is more, so it relaxes faster. If they are far away, it relaxes slowly. It is exactly what happens when you see the carbon 13 NMR. If you try to measure the T1 of the spin lattice relaxation time by some experiment in carbon 13, carbons which are attached to proton relaxes faster. Carbons which are not attached to proton relaxes very slowly. This is a phenomena you should understand. The neighboring spins, if they are present, the dipolar interaction will become better. The dominant interaction aids this relaxation of the nuclear spins. Okay. So this is another thing. Usually the directly bound protons and others will cause relaxation in carbon 13 spins, and if they are absent, relaxation will be different, or if they are far away separated in the molecular structure, then also relaxation is slow. So this is a picture which shows about the dipolar interaction way back, which published very, very long back in the very first earlier days, when the small molecule, how the T1 comes here, as if it keeps on increasing the higher magnetic field, T1 depends also on the magnetic field, okay. And this is for the larger molecules here. And in the case of the solid, you see T1 becomes even larger, okay. So that's the, here T2 is very large, T1 is the red color. So as a function, as you keep on increasing with respect to correlation time, then here it becomes larger and larger. Here also T1 is larger, in between it is smaller. On the other hand, the T2 keeps on changing. When it becomes go to the solid situation, T2 will be so this thing very rapid, whereas T1 will be very, very long. So that's what is going to happen in the case of solids. So that's the thing which I wanted to tell you more about the relaxation phenomena. There are several other relaxation phenomena. So dipole relaxation can arise from the interaction of the nuclear spins with an unpaired electron also. If there is an unpaired electron, remember electron magnetic moment is nearly 600 times more than that of the proton. So it is an efficient source of relaxation. That is why if there is an unpaired electron, paramagnetic species, such nuclei relaxes very fast. So this is called a paramagnetic relaxation mechanism is there. And if you have a unpaired electron in your molecule, sometimes it is very difficult to get sharp lines. The nuclear spins relaxes very fast. Its resident time in the excited state is very small. The signals will become very, very broad. Of course, because of uncertainty principle, which we discussed this in the very first course itself. So even the presence of the dissolved oxygen, because oxygen itself is paramagnetic, that can also contribute to spin relaxation. So there are certain things, all these things contribute for relaxation because of the dipole-dipole interaction. Now there are some ways can we reduce this. There are certain things. If the T1 is sufficiently long, let us say, very long T1, I want to do the experiment faster. Sometimes T1 is of the order of millisecond, microsecond or hours and days. How do I do that? There are ways of reducing the T1 called relaxing agents, relaxation agents. For example, we can use chromium acetate which is called CRACAC. We can use CRACAC in organic solvents. Addition of a micro quantity, now you do not add kilos of that, then you will not be able to get the spectrum. Micro quantity of this will interact with your molecule of interest and then aids in relaxing. The spins will relax faster. Sometimes we use magnesium chloride, various things we can use. And all these things are relaxing agents, reduce relaxation time and helps you in speeding up your data acquisition. Your experiment becomes faster. Okay. So this is what is about the relaxation to dipole-dipole interaction. Next class I will discuss about various other relaxation mechanisms quickly, and then we will go about measurement of the T1 and then discuss T2 and then measurement. Quickly we will do that. So now there are a few other relaxation mechanisms like CSA, spin rotation, quadrupole relaxation, etc. We will come to that later. But today right now what I was trying to say is major dominant interaction phenomenon was dipole relaxation, dipole-dipole interaction. So this is what we discussed today about various phenomena related to relaxation mechanism, concept, how the energy gets dissipated, how the fluctuating fields are produced, what is the frequency of the fluctuating field, how it is different from the RF field applied, both are at Larmor frequency, how it affect different, everything we understood. We correlated them with the spectral density function, with the correlation time T or tau C, which again to do with the size of the molecule, and then how spectral density function affects different molecules for slow motion, intermediate motion and fast motion. All those things we discussed a lot. And the relaxation mechanism, we discussed about the dipole-dipole relaxation, which is the dominant source of relaxation. I said when the two spins are there, there is a dipolar interaction. The orientation with respect to the external magnetic field B0 do not change. However, orientation between them change because the spins keeps on changing its orientation. As this molecule is undergoing fluctuation, the orientation between these things, the fluctuating field at the side keeps on changing, and that can induce relaxation if it is at the Larmor frequency. So all these things we discussed, and then the relaxation phenomena can be reduced, relaxation speed can also be, relaxation can be enhanced by using external agent called CRACAC and others, and these are the dipole relaxation mechanism. Now we will come to the other relaxation mechanism in the next class. Starting with CSA, we will discuss other things. So I will stop here today. We will come back with other relaxation mechanism discussed later in next class. Thank you very much.